Assalamualaikum warahmatullahi wabarakatuh. This is chapter 20, Magnetic Properties. First of all, I would like to ask, why do we need to study the property of magnetic materials? And what is the importance of magnetism in our daily life? For the first question, well, it is because magnetic materials play a crucial role in the progress of industrial development and scientific growth. Examples of magnetic materials are transmission, electronic devices, analog and digital data storage, medical devices, sensors, and more. So, how do we connect the importance of magnetism in our daily life? These are the examples. We used to make a tight seal on the doors of refrigerators and freezers, the power speakers and stereos, earphones and television. Magnets are used to store data in computers and important in scanning machine called MRI, which is magnetic resonance imagers. So let's proceed of what is magnetism. Magnetism is a physical phenomenon produced by the motion of electric charge resulting in attractive and repulsive forces between objects. That is how magnetism works, which is we already know that for years, but still we are not aware about its principles and mechanism. So now, in this topic, or let's say presentation, we will discuss about its properties, principles, and mechanism. So let's start on magnetic dipoles. Magnetic dipoles, generally a tiny magnet of microscopic 2 subatomic dimensions, equivalent to flow of electric charge around a loop. Magnetic dipole, generally a tiny magnet of a microscopic to subatomic dimension. So kung titingnan natin yung figure, dyan tayo mag-base. Kung nasaan yung flow ng electric charge around the loop, which is this one. So, magnetic dipole is a magnetic north pole, this, and magnetic south pole, separated by a small distance. Magnetic dipole moments have dimensions of current times area or energy divided by magnetic flux density. Magnetic field vectors. So here we will describe magnetic behavior in terms of several field vectors. The externally applied magnetic field, sometimes called the magnetic field strength, which is designated by H. So in this figure, in this figure A, the magnetic field is H as generated by cylindrical coil is dependent on the current, which is the I, the number of turns, which is the N, and the coil length, which is this. According to the previous equation, the magnetic flux density B sub O in the presence of a vacuum is equal to this, where 0 is the permeability of vacuum. So in the figure letter B, the magnetic flux density B within a solid material is equal to H, this one, where is the permeability of the solid material. So we are going to discuss the magnetic units and conversion factors for the SI and CGS EMO systems. So the magnetic induction will be, or let's say magnetic flux density, denoted by B, represent the magnitude of the internal field strength within a substance that is subjected to the H field. Next is the magnetic field, which is denoted as H. Next is the magnetization, which is another field quantity denoted as M, is a solid that defined by the expression. Next is the permeability of vacuum, which is denoted by this. A universal constant which has value of 4107 H over M, or is equal to 1 mO. Next is the relative permeability, denoted by this, and it is unitless. Lastly, the susceptibility, which is unitless. The magnetic susceptibility and relative permeability are related. So let's proceed to origin of magnetic. The macroscopic magnetic properties of materials are a consequence of magnetic moments associated with individual electrons. Some of these concepts are relatively complex and involve some quantum mechanical principles beyond the scope of this discussion. Consequently, simplifications have been made and some of the details omitted. So, as shown in the figure, this is a demonstration of the magnetic moments associated with the figure A, an orbiting electron, and for the figure B, a spinning electron. An electron may be considered to be a small current loop generating a very small magnetic field and having magnetic moment along its axis of rotation, as schematically illustrated in this figure. So next is diamagnetism. Diamagnetism results from change in electron orbital motion that are induced by an external field. The effect is extremely small, with susceptibilities on the order of 105 and in opposition to the applied field. All materials are diamagnetic. Diamagnetism is actually very weak form of magnetism that is induced by a change in the orbital motion of electrons due to applied magnetic field. This kind of magnetism is non-permanent and persists only in the presence of an external field. So let's proceed on the figure. So as you can see, the figure A is the atomic dipole configuration for a diamagnetic material with and without a magnetic field. In the absence of an external field, no dipoles exist. In this presence of a field, dipoles are induced that align opposed to the field directions. So for the figure B, this is an atomic dipole configuration with and without an external magnetic field for a paramagnetic material. So before we discuss this figure, what is paramagnetic? It is a material that does having permanent atomic dipoles, which are acted on individually and aligned in the direction of an external field. So let's back to the figure. As shown in the figure, these atomic dipoles are free to rotate, and paramagnetism results when they preferentially align by rotation with an external field. So the difference between the paramagnetic and diamagnetic is that paramagnetic is permanent dipole moment, or let's say permanent magnetic moment. Unlike the diamagnetic, it is not permanent dipole moment. So we can proceed now in this diagram. I mean figure. Diamagnetic and paramagnetic materials are considered non-magnetic because the magnetization are relatively small and persist only while an applied field is present. So in this figure, it is the schematic representation of the flux density B versus the magnetic field strength H for diamagnetic and paramagnetic materials. So in these magnetic responses differ greatly in strength. Diamagnetism is a property of all materials in opposes applied magnetic fields, but is very weak. Paramagnetism, when present, is stronger than diamagnetism and produces magnetization in the direction of the applied field and proportional to the applied field. Both of it material are considered non-magnetic because they exist magnetization only when in the presence of the external field. Also, for both, the flux density B within them is almost the same as it would be in a vacuum. So let's proceed. Ferromagnetism. Ferromagnetism is a certain metallic materials possess a permanent magnetic moment in the absence of an external field and manifest very large and permanent magnetization. That is the characteristic of ferromagnetism. So, it is a large and permanent magnetization may be established within the ferromagnetic metals, which is an element of Fe, Co, and Ni. Atomic magnetic dipole moments are of spin origin, which are coupled and mutually aligned with moments of adjacent atoms. So, in short, it is a permanent magnetic moment in ferromagnetic materials result from atomic magnetic moments due to the uncancelled electron spin as a consequence of electron structure. There is also an orbital magnetic moment contribution that is small in comparison to spin moment. Furthermore, in a remember that in a ferromagnetic material, coupling interaction cause net spin magnetic moments of adjacent atoms to align with one another, even in the absence of external field. So in this figure, it illustrates a mutual alignment of atomic dipoles for a ferromagnetic material, which will exist even in the absence of an external magnetic field. The saturation magnetization is equal to the product of the net magnet moment for each atom and the number of atoms present. For each of iron, cobalt, and nickel, the net magnetic moments per atom are 2.22, 1.72, and 0.60 Bohr magnetons respectively. So now let's move to anti-ferromagnetism. This phenomenon of magnetic moments coupling between adjacent atoms or ions occurs in material other than those that are ferromagnetic. In one such group, this coupling results in an anti-parallel alignment. The alignment of the spin moments of neighboring atoms or ions in exactly opposing directions is termed antiferromagnetism, which is this means it is opposing magnetic moments cancel one another, and as a consequence, the solid as a whole possesses no net magnetic moment. So, now let's proceed to ferrimagnetism. Some ceramics also exhibit a permanent magnetization, termed ferramagnetism. The macroscopic magnetic characteristic of ferromagnets and ferromagnets are similar. The distinction lies in the source of the net magnetic moments. There are antiparallel spin coupling interaction between the Fe ions, similar in the character of antiferromagnetism. However, the net ferrimagnetic moment arises from the incomplete cancellation of spin moments. The principles of ferrimagnetism are illustrated with the cubic ferrites, where cubic ferrites have the inverse spinel crystal structure, which is cubic in symmetry and similar to the spinel structure, where a unit cell of inverse spinel structure is shown on front cover of the book. So in this diagram, it shows the spin magnetic moment configuration of F to the power of 2 and F to the power of 3 ions in Fe304, which the blue sphere stands for the O2, and for the red, green, yellow sphere stands for the Fe2 plus, Fe3 plus. This inverse spinel crystal structure might be thought of as having a generated by the stacking of close packed planes of O2 ions. Again, there are two types of position that may be occupied by the iron cations as illustrated in the last figure. For one, the coordination number is 4, tetrahedral coordination. That is, each Fe ion is surrounded by 4 oxygen nearest neighbors. For the other, the coordination number is 6, octahedral coordination, with the inverse spinel structure half the trivalent. Ions are situated in octahedral positions and the other half in tetrahedral positions. So any ferromagnetic or ferrimagnetic material that is at the temperature below is composed of small volume regions in which there is a mutual alignment in the same direction of all magnetic dipole moments, as illustrated in this figure. The schematic depiction of domains in a ferromagnetic or ferrimagnetic material. These arrows represent atomic magnetic dipoles. With each domain, all dipoles are aligned, whereas the direction of alignment varies from one domain to another. So kaya siya ganyan. Okay, so what is this domain? Domain, a total saturation. The entire solid is a single domain, and the magnetization is aligned with the field direction. The change in domain structure with increase or reversal of magnetic field is accomplished by the motion of domain walls, both hysteresis, the lag of the B field behind the applied H field, as well as permanent magnetization or remanence result from the resistance to movement of the domain walls. So, the adjacent domains are separated by domain boundaries or walls, across which the direction of magnetization gradually changes. Normally, domains are microscopic in size, and for a polycrystalline specimen, each grain may consist of more than a single domain. Thus, in a microscopic piece of material, there will be a large number of domains, and all may have different magnetization orientations. The magnitude of the M field for the entire solid is the vector sum of magnetization of all domains, each domain contribution being weighted by its volume fraction. For an magnetized specimen, the appropriately weighted vector sum of magnetization of all the domains is 0. So let's proceed to this. A high hysteresis effect is produced in which the B field lags behind the applied H field. Yan yung diniscuss natin ngayon na. Or decrease at a lower rate. A zero H field, point R on the curve, there exists a residual B field that is called the remanence, or remanent flux density. B sub R, the material remains magnetized in the absence of the external H field. To reduce the B field with the specimen to 0, a H field of magnitude H sub C must be applied in the direction opposite to the original field. The H sub C is called the correctivity, or sometimes the coercive force. In the figure, the magnetic flux density versus the magnetic field strength for a ferromagnetic material that is subjected to forward and reverse saturation from point S and S, a point sub S. The hysteresis loop is represented by the solid curve. The dashed curve indicates the initial magnetization. The remanence B sub R and the coercive force H sub C are also shown. From saturation point S in this figure, the H field is reduced by reversal of field direction. The curve does not retrace its original path. A hysteresis effect is produced in which the B field lags behind the applied H field, or decreases at a lower rate. At 0, H field at the point R on the curve, there exists a residual B field that is called the remanence, or the remanent flux density, which is the B sub R. The material remains magnetized in the absence of the external H field. So now let's proceed to magnetic anisotropy. So the magnetic hysteresis curves discussed in the previous section will have different shapes depending on the various factors. What are these factors? Whether the specimen is a single crystal or polycrystalline. Second, if polycrystalline, any preferred orientation of the grains. Third, the presence of post or second phase particles. Fourth, other factors such as temperature. And if mechanical stress is applied, the stress state. So we have here the example where the B versus H curve for a single crystal of ferromagnetic materials depends on its crystallographic orientation relative to the direction of applied H field. This behavior is demonstrated in this figure. So, as you can see, the magnetization curves for single crystal of iron and nickel. For both metals, a different curve was generated when the magnetic field was applied in each of crystallographic direction. For the next figure, magnetization curves for a single crystals of cobalt. The curves were generated when the magnetic field was applied in 001 and 1010 over 1120 crystallographic direction. The crystal of nickel and iron, where the magnetizing field is applied in 100, 110, and 111 crystallographic direction. In this figure for cobalt in 0001 and 1010, 1120 direction. This depends of magnetic behavior or on crystallographic orientation is termed magnetic or sometimes magnetocrystalline anisotropy. I'm sorry. For each of these materials, there is one crystallographic direction in which magnetization is easiest. That is, saturation is achieved at the lowest H field. This direction is in as much as saturation occurs at point A, whereas orientation saturation points corresponds respectively to the point B and C. Let's proceed to soft and hard magnetic materials. The size and shape of hysteresis curve for ferromagnetic and ferrimagnetic material is of considerable practical importance. The area within a loop represents a magnetic energy loss per unit volume of material per magnetization, demagnetization cycle. So, in this figure, it shows the magnetization curves for soft and hard magnetic materials, which both ferromagnetic and ferrimagnetic materials are classified as either soft or hard on the basis of their hysteresis characteristic. So let's start with the soft magnetic materials. It is used in devices that are subjected to alternating magnetic fields and which energy loss is most below. One familiar example consists of transformer cores. For this reason, the relative area within the hysteresis loop must be small. It is characteristically thin and narrow, as represented in this figure. Consequently, a soft magnetic material must have a high initial permeability and low corrosivity. A material possessing this property may reach in saturation magnetization with a relatively low applied field and still has low hysteresis energy losses. So now let's proceed to hard magnetic material. Hard magnetic materials are used in permanent magnets which must have a high resistance to demagnetization. In terms of hysteresis behavior, a hard magnetic material has a higher remanence, corrosivity, and saturation flux density. The two most important characteristics relative to application for this material are the corrosivity and what is termed the energy product, designated as VH max, submax. This energy product corresponds to the area of the largest BH rectangle here, as shown in the figure, that can be constructed within the second quadrant of the hysteresis curve. Its units are kilojoule per meter cube. The value of the energy product is representative of the energy required to demagnetize a permanent magnet. That is the larger BH max, the harder the material in terms of its magnetic characteristic. So, in this figure, it shows the magnetization curve that displays hysteresis within the second quadrant. Here, are drawn to the BH energy product rectangles. This is our energy product where denoted as BH max. The area of the rectangle labeled BH max the largest possible, which is greater than the area of the defined by the B, D, and the HD. This. Again, hysteresis behavior is related to the ease with which the magnetic domain boundaries move. By impending domain motion, the correctivity and susceptibility are enhanced, such the large external field is required for demagnetization. Furthermore, these characteristics are interrelated to the microstructure of the material. Magnetic storage. The information storage is accomplished using magnetic materials. The two principal types of magnetic media are hard disk drives and magnetic tapes. The storage medium for hard disk drives is composed of nanometer size grains of an HCP cobalt chromium alloy. These grains are oriented such the direction of easy magnetization is perpendicular to the plane of the disk. For tape memory storage, either needle-shaped ferromagnetic metal particles or plate-shaped ferromagnetic barium ferrite particles are employed. Particle size is on order of tens of nanometers. So in this diagram, a hard disk drive that employs the perpendicular magnetic recording medium, also shown are inductive write and magnetoresistive read heads. In essence of computer bytes, sound or visual images in the form of electrical signals are recorded magnetically on very small segments of magnetic storage medium. So the above and in close proximity to the magnetic medium by self-generating air bearing as a medium passes beneath at relatively high rotational speed. On the other hand, tapes make physical contact with the heads during read and write operation. Tape velocities run as high as 10 meters per second. As noted previously, there are two principal types of magnetic media, which is the hard disk drives and the magnetic tapes, both of which we now briefly discuss. So next, let's proceed to superconductivity. This will be the last subtopic of this chapter. As most high purity metals are cooled down to temperature nearing 0 Kelvin, the electrical resistivity decrease gradually approaching some small yet finite value that is characteristic of particular metal. There are few materials, however, for which the resistivity at a very low temperature abruptly plunges from a finite value, one that is virtually zero, and remains there open further cooling. Materials that display this later behavior are called superconductors, and the temperature at which they attain superconductivity is called the critical temperature. So as you can see in the diagram, the temperature dependent on the electrical resistivity for normally conducting and superconducting material in the vicinity of 0 Kelvin. At temperature below the superconductivity, the superconducting state will cease upon application of sufficiently large magnetic field, termed the critical field, which depends on the temperature and decrease with increasing temperature. The same way be said for current density, that is critical applied current density exists below which a material is superconductive. So as you can see here in this figure, the critical temperature, current density, and magnetic field boundary separating superconducting and normal conducting states. And for this figure, at this figure A, the superconducting state, a body of material circle, includes a magnetic field arrow from its interior. So ito, pumasok siya doon. And then doon naman sa figure B, the magnetic field penetrates the same body of material once it becomes normally conductive. So the superconductivity phenomenon has been satisfactorily explained by means of a rather involved theory. In essence, the superconductive state results from attractive interaction between pairs of conducting electrons. The motion of these paired electrons became coordinate such the scattering by thermal vibration and impurity atoms is highly inefficient. Thus, the resistivity being proportional to the incidence of electron scattering is 0. That's all for the chapter 20 magnetic properties. Thank you.